Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the honors students of physics, and in the last few lectures we have been discussing the various sections in optics, namely interference, diffraction, etc. In this lecture we will be talking about comparison of a zone plate with a convex lens, and again the diffraction effects arising due to the light passing through a circular aperture and then at a straight edge and so on. So, this is lecture 35. The contents are difference between zone plate and a convex lens, distinction between interference and diffraction, Fresnel and Fraunhoffer types of diffraction, diffraction at a circular aperture. In the slide which I am showing now, on the right you have got the zone plate, on the left you have got convex lens. There are a lot of things which are analogous to the zone plate and a convex lens. You all know what is a zone plate. In the previous lectures we saw how to construct a zone plate. You take a piece of paper and draw circles with the radii, as I told you in the previous lecture, the square root of n lambda, square root of 2n lambda, 3n lambda, integral multiples of lambdas, that is the radii of the various circles. So, then what you do is you darken the alternate circles, so that light is passing through the alternate zones. Supposing you darken the central circle, that is the zone 1, light will be allowed by zone 2, then again zone 3 will not allow, it is darkened, zone 4 will allow. Therefore, you have a series of zones through which light will be allowed, and the other series of zones 1, 3, 5 will not allow, whereas 2, 4, 6 will allow the light to be transmitted. This is the so called zone plate. You all know by now lot of things about convex lens. In the case of convex lens, you write the focal length in terms of the radii of curvatures R1 and R2, and you all know that for a point source you get a point image. The source here, you got the lens here, you got the image here, a point source on the optic axis, you get a point image on the optic axis, that is the lens you have. Then for a white light that you got here, the source white light, you will be having all the colors. As I told you in the last lecture also, the violet will come to a focus at a point nearer to the lens surface, whereas red will be coming to a focus at slightly far off distance. By this what I mean is there will be chromatic aberration. All the colors will not come to a focus at the same point in the case of a convex lens, and also in the case of zone plate. Let us now see in detail the differences or the comparison between a zone plate and a convex lens. Both the zone plate and convex lens form real images of the object, and the equations connecting the conjugate distances are similar. That is, you have u and v, the distance separating the source and the lens. Similarly, lens and the image, they are the distances. The focal length of both depend on the wavelength, that is what I mean by chromatic aberration, and hence suffer from chromatic aberration. The chromatic aberration in a zone plate is much more severe than in a convex lens. Then a zone plate acts simultaneously as a convex lens and a concave lens. In addition to a real image, a virtual image is also formed simultaneously. A convex lens forms only a real image. In the case of zone plate, the image is formed by the phenomenon of diffraction. Then I will ask the question, how do you get the image in the case of a convex lens? You have got an object here, you have got a lens here. The image is obtained by the phenomenon of what? Reflection, interference, or diffraction. What? You have to tell the answer. It is due to refraction. Light rays pass through the lens, they are getting refracted at within the lens, and then the final image is obtained. Therefore, in the case of a lens, it is refraction, whereas in the case of zone plate, the image is obtained by the phenomenon of diffraction. Okay, this is what I am having here. In the case of a convex lens, the image is formed due to refraction of light. The zone plate has got multiple foci on either side of the plate. Hence, the intensity of the image formed will be much less. Convex lens has only one focus. As all the light is focused at one point, the intensity of the image will be more. In a zone plate, waves reaching the image point through any two alternate zones differ in a path difference by lambda or a phase difference of 2 pi. You know, the light is passing through a zone, then the next zone will not allow, only the next zone will allow. So, the path difference will be lambda. You know, why is it called zone plate? Zone plate or half period zones. Half period zones means light coming from two consecutive zones will differ by time differences half. That is the reason why it is called half period. If time difference is half, that means crest and trough will meet, or a path difference will be lambda, and lambda by 2. The first and third will differ by lambda, first and second will differ by lambda by 2. So, now we are talking about light coming through the first zone and the third zone. Therefore, the path difference between light coming from first and 3 will be having a path difference lambda or a phase difference of 2 pi. In the case of a convex lens, all the rays reaching the image point have 0 path or phase difference. A zone plate can be used over a wide range of wavelengths from microwaves to X-rays, whereas the convex lens means you have the usual light. For instance, the light wave, that is a light wave that one can see from 4000 angstroms to 7000 angstroms. Glass lens cannot be used beyond the visible region. So, now we will pass on to the next section. So far, we have been talking about a comparison between what? The zone plate and a convex lens. Now, we will try to compare between the interference bands and diffraction bands. We saw in the lectures which I delivered much earlier about interference bands which are formed by what are the methods? The Fresnel biprism or Newton's rings, or what? Fresnel biprism or Newton's rings or air wedge. Now, there are very many instances wherein you come across interference bands. Similarly, you get diffraction bands. Now, how do you compare the interference bands with the diffraction bands? So, with regard to interference, it is a result of interaction of light coming from different wavefronts originating from the same source. You have the Young's double slit experiment where light is coming from a single source, then you got two slits S1 and S2, they interfere with each other and so on. Diffraction is the result of interaction of light coming from different parts of the same wavefront. Interference fringes may be or may not be of the same width. In general, interference bands will be of the same width, which I will show you a bit later, whereas diffraction fringes are not of the same width. That also I will show later. A region of minimum intensity are perfectly dark. You know, in the case of Newton's rings and certain other cases, you will have bright and dark bands, bright band, dark band, bright band, dark band. So, perfect bright band, perfect dark, perfect bright, dark. They are equispaced. All the bands are of the same intensity, and again the distances separating any two bands, any two bright bands or any two dark bands, the distances will be the same, that you call as the band width. But here in the case of the phenomenon of diffraction, the intensity of the light that you get on the region where the diffraction occurs on the screen, you see the intensities will be fading. You have got the primary maximum and you have got the minima, the intensities will be differing, and again there is no such thing as bandwidth, because you have the intensity maximum here that comes down, and again the next intensity will not be the same as the earlier intensity. The intensity of the band of maybe 1 and 2 will not be equal. 3 will be much less, smaller or lesser, less intense, and therefore the diffraction bands will not be equispaced, and again the intensity will not be having the same values, whereas interference bands, all the bands will be of the same intensity. Okay, you see here I am giving you the figurative representation of what I have told you. This is the interference pattern you get on the screen. This is the interference pattern. Okay, you know by now how you get the interference pattern. You have got a source of light. There are two slits which act as two coherent sources. You get the maximum intensity giving rise to a bright line, then the minimum intensity giving rise to dark line. Now, what are the points that I told you? The bands that you get or the fringes that you get are of same intensity, right? The intensity of the bands will be of the same magnitude. Okay, here you have got bright and the dark bands, they are dark. Okay, what is the second point? The width of all the bright bands, right? The width of the band and the width of this band, width, all the widths of the bands will be the same, and again the width of the dark band will be equal to width of the bright band. So, hence you can call beta. What is beta? It is called a bandwidth. How do you define the bandwidth? Distance between two successive bright bands. So, you got a bright band, you take the center here, when they are sharp, this much is the thickness is shown for the sake of understanding, but you will be having in air wedge or Newton's rings sharp bands. So, when you have a sharp line, the distance separating the two sharp lines is the bandwidth. Similarly, distance separating two dark lines is the bandwidth. So, this bandwidth will be the same. What is bandwidth? The distance that separates two bright lines, two consecutive bright lines. Similarly, the distance separating two consecutive dark lines is known as the bandwidth, and this bandwidth will be having a unique value in the case of interference pattern. Let us now pass on to the pictures which will make you to understand the diffraction pattern. Now, the diffraction pattern of a circular aperture. What do you mean by circular aperture? That we are going to discuss in detail. Now, light is made to pass through an aperture. You got a source of light. This is a circular aperture, a hole. In a sheet of paper, you drill a hole. Light is allowed to pass through it. You have a screen here. On the screen, you will be getting a pattern like this. This is a so-called diffraction pattern. Diffraction at a circular aperture. This is a diffraction pattern. At this point, we will have a short break. welcome back at the break. I have been telling you before the break, passing through a circular aperture. When light is allowed to pass through a circular aperture, you get a pattern that can be seen on the screen, or you can use a telescope and see the diffraction pattern. So, the diffraction pattern of a circular aperture consists of a bright central disk. You got a bright region here, surrounded by concentric bright and dark rings. You got a bright ring here, dark ring here, bright ring here, and I think I will go to the next slide. You see here, when you have a blade in the path of the light beam, you have to carefully see, right? You should have something like X-ray eyes. You have to carefully see when you got a blade, or even a sheet of paper, or even you can have your dress material, a dhoti or some kind of thing. You have in the path of the light beam very near to the edge, the light beam will be bending. That is known as the phenomenon of diffraction. What is diffraction? It is nothing but the bending of the light beam. So, because of it, there will be a series of bands, they call the diffraction bands, and the bands will be having this kind of shapes similar to the blade, but bright, dark, bright and dark. Now, the intensities will not be the same, and again the distances separating the bands also will not be the same. Okay, that is nature of what we call as diffraction bands, wherein the maximum will be there, next maximum will be much lesser, and the distances separating any two maxima will not be the same as any other two maxima considered on the screen or observing through a telescope. Now, we will pass on to have an understanding of what we mean by Fresnel diffraction and Fraunhoffer diffraction. They are very important. The Fresnel and Fraunhoffer types of diffraction. The diffraction phenomena are broadly classified under two types, the Fresnel diffraction and the Fraunhoffer diffraction. You see in the next slide, you have the source here, the slit is here, the light is made to pass through the opening or the slit. It is coming to a focus on the screen. You do not have any condensing lens, right? No, you do not have any condensing lens. So, what is the difference between the picture A and figure B? You have a condensing lens here, which makes the light rays to pass through the slit. They are again made to condense or converge and getting into a focus at a point P here. So, you make use of lenses in the second case. So, first comes the Fresnel diffraction. In this type of diffraction, the source of light and the screen are effectively at finite distances. This is a very important point. At finite distances from the obstacle. What is obstacle? Obstacle is something here. You got a slit here or aperture here. It may be a straight edge. Straight edge means what? You can take this is a straight edge. Light is passing the thing. I showed you the work done by Grimaldi. Grimaldi, the person who observed the phenomenon of diffraction. So, when light is incident, when light is coming here, you have got an obstacle in the path of the light beam. Here, you do not have any obstacle. So, light will go directly and fall on the screen. The entire light intensity will be seen on the screen, but here light is being cut by this obstacle. Okay. So, you should have complete darkness here. On the contrary, because light beam is bending, that is you have got diffraction. So, within the shadow region also there will be some intensity that you call as diffraction. So, this is obstacle, right? This is obstacle, and or you can have an aperture, or you can have a slit and so on. These cases we are going to discuss in the lectures to come. Therefore, this is a Fresnel diffraction. A is the Fresnel diffraction, wherein the distances should be finite, and observation of Fresnel diffraction phenomenon does not require lenses. You do not have lenses here, right? On the contrary, you go to Fraunhofer type of diffraction. You have here the incident wavefront is not planar. As a result, the phase of the secondary wavelets is not the same at all points in the plane of the obstacle. the resultant amplitude at any point on the screen is obtained by the mutual interference of the secondary wavelets from different elements of unblocked portions of the wavefront. This is what we are seeing with regard to Fresnel diffraction. Okay. Now, whatever I have told you now, they correspond to Fresnel diffraction, whereas in Fraunhoffer type, as I told you, you got lenses and a few other things we want to say are given here. In Fraunhoffer diffraction, the source and light, the source of light and the screen are effectively at infinite distances from the obstacle. Fraunhoffer diffraction pattern can be easily observed in practice. The conditions required for Fraunhoffer diffraction are achieved using two convex lenses. As I show here, you can see the pattern that you get on the screen by having two lenses, right. You have got a lens here which makes the light rays to become parallel, right. Then the diffracted light rays which are passing through the opening or the slit, they are made to converge at a point P, the convergent lens you got here, so that the diffracted light rays are made to converge or come to a focus at a point P. So, you got lenses in the case of Fraunhoffer diffraction. Okay. So, then the distances are infinite. Fraunhoffer diffraction pattern can be easily observed in practice. The conditions required, as I told you, are two convex lenses. One to make the light source, the first lens, it makes the light source to be made parallel to, that means light rays are made to become parallel, that is what I show here. Then the second lens, what it does, as I told you, it makes, it's called a condensing lens. It makes the light rays which have undergone diffraction, these diffracted light rays, you know, the angle theta is shown here. If the diffraction does not occur, then the light ray would have gone in this direction. It does not suffer diffraction. Now, because of diffraction, the light takes a different route, because the angle of theta, theta is what? You have seen the diffraction grating, we have studied diffraction at a greater depth. So, theta is the angle of diffraction. So, this is the angle of diffraction theta here. So, the diffracted beam or the diffracted light rays are made to converge by a convergent lens. That is what I am trying to tell you here. So, one to make the light rays to become parallel, the other one to obtain diffraction beam on the screen, the condensing lens. The diffraction is thus produced by interference between parallel rays. Whether you have talk of diffraction or interference, finally, the light rays should come to a focus. Therein, you come across again interference, you come across constructive interference. In all the cases, you say the path difference should be integral multiple of lambda if you want to see brightness at a particular point. At any given point, if you want to have a bright band or a bright fringe, you talk of path difference, and the path difference, as all of you know by now, it will be n lambda. That means crusts meet each other or troughs meet each other. The incident wavefront as such is the plane, and the secondary wavelets which originate from the unblocked portions of the wavefront are in the same phase at every point in the plane of the obstacle. This problem is simple to handle mathematically because the rays are parallel. The incoming light is rendered parallel with a lens, as I showed you just now, and the diffracted beam is focused on to a screen with another lens, which usually you call as a convergent lens. Now, we will move on to another subsection, because we have been talking about diffraction, and I showed the opening, a slit. In the case of diffraction, you can have diffraction of light by means of a circular aperture or a rectangular aperture, or diffraction at a wire, diffraction at a straight edge. These things I will deal with in a greater detail in the time to come, but the point is, first you go to the case of diffraction at a circular aperture. What do you mean by circular aperture? You make a hole in a cardboard or in the path of the light beam. What you make is the light ray is made to pass through an opening. a circular opening is called a circular aperture. You see the diagram, what are A, B, S, P, all these things are to be known. So, A, B, you got a source here, you see a small opening here at the point O, around the point O you got an opening, right. That refers to a circular aperture. Now, what is happening will be shown with greater degree of clarity in the pictures to come. You see an incident light beam coming from a source, you see a hole here. By aperture or a big thing, whatever I am talking, is not a big deal. You got a light beam here, as I told you, put a blade, you get the diffraction pattern. Similarly, in the case of, instead of having a blade or a straight edge, you can call this a straight edge, right. So, the light beam is cut off by partially by putting a block, right. So, what happens to the light in the shaded region? So, similarly here you have a circular aperture, as I told you earlier. Now, the light that is coming here undergoes the angle of diffraction. Essentially, what you do is, when light is allowed to pass through a circular opening, what kind of pattern you get on the screen? In the screen, you do not have uniform light. The point is, you got an aperture here, opening here. It does not mean, if Newton's theory is right, then what should happen is, you got an opening here, then you should have got a circular patch with what? Bright patch or dark patch, where light is coming. So, you should have a bright patch, because the opening here, if you believe in Newton's corpuscular theory of light, or you believe in Newton's ray concept, the geometrical optics, then this region should be bright. You should have only bright region alone. On the contrary, you got bright and dark rings, bright and dark regions. That is the so called diffraction at a circular aperture. And let me show you one or two other slides again. The light is coming here and passing through the aperture, as is shown here. What you get is, you get a bright region, right. Because it is bright, the intensity is large, right. This is a bright. This is what I told you earlier also. When you have a diffraction phenomenon, you see the intensity is large, then the next intensity is here, right. So, the intensity from here is again large, not much larger as you have got here. It is here, then the intensity here will be much lesser. You see, the point is, the intensity is larger, it is slightly much lesser and much lesser. But in the case of interference bands, all the three, say 1, 2, 3 should be of the same intensity. Let me now summarize what I told you in this lecture. The summary goes as follows. Both the zone plate and convex lens form a real image of the object, and the equations connecting the conjugate distances are similar. So, this gives the similarity between the lens and the zone plate. The focal lengths of both depend on the wavelength lambda, and hence suffer from chromatic aberration. That is, the image suffers from chromatic aberration. Interference fringes are the same width, but and again the brightness is the same. The problem of diffraction at a circular aperture is treated on the basis of dividing the wavefront into half period zones. Let me now ask you a few questions to see whether you understood something from this lecture. The questions are: explain the differences between the zone plate and a convex lens. How are interference bands differ from diffraction bands? What are the differences between Fresnel diffraction and Fraunhoffer diffraction? With this, we come to the end of this lecture, and in the lectures to come, we will continue with the problem of diffraction at a circular aperture and other kinds of openings like narrow slit, straight edge, and so on. Thank you.